Okay, so today we're going to look at what we call a BLEU. So the idea is we want to estimate the population mean of some data. And before this course, you've been told the sample mean is a really good thing to do. In fact, it's going to be what we call the BLEU. And what do we mean by BLEU? It's the best linear unbiased estimator. So we take an estimator. So this is a function that will take data and return a number. It's unbiased, so the expected value of that will be the thing we're interested in. In our case, the population mean, we'll call it mu. It's linear, so it's a linear combination of that data, and it's best. That is, when it comes to all the ones you consider, it has the lowest variance. So we're going to show the sample mean is the thing to do. So here's my little theorem. We've got y1 up to yn, they're IID random variables, so they all have the same distribution, they're independent of one another. We know that the expected value of each of these yi's is mu, and the variance is sigma squared. And we know that the BLEU, the best linear unbiased estimator for mu, the population mean, is given by the sample mean. Add them all up, divide by how many. So we're going to have to prove this. Now, a couple of things we're going to need before we start. First of all, I want to write that the variance of the sample mean, just remember, is sigma squared on n. Done. So I want you to keep that in mind, because the trick we're going to do is we're going to think of a general form of a BLEU, sorry, not a BLEU, but a linear unbiased estimator. And we're going to calculate its variance, and then we're going to show its variance is equal to that number we just wrote plus some extra non-negative stuff, and hence it's a lower bound. And this is a common trick that we use. So let's consider an arbitrary estimator, which I call t. There's going to be some sort of linear combination of the data. So I equals 1 to n, yi. So this is a linear, unbiased estimator. Easy. Well, as I said, we're going to look at the variance of this. Well, what's the variance of t? Well, because these are all independent, we can write this as I goes from 1 to n, ai squared, the variance of yi. And we know the variance of y equals sigma squared. So this is going to be sigma squared, summation as I goes from 1 to n, ai squared. Now, I want to get this in terms of the variance of the sample mean plus some stuff. So I'm going to do a classic trick here. I'm going to write this as sigma squared, summation as I goes from 1 to n. I'm going to write ai, and I'm going to take off 1 on n and plus 1 on n squared. So all I've really done here is I've added 0, because I've added and taken off the same thing. So now we can expand this, and we will basically get that this is equal to sigma squared. We've got the summation as ai minus 1 over n squared, I equals 1 to n, plus 2n, summation of ai minus 1 over n, which is the cross product, plus the summation as I goes from 1 to n, 1 over n squared. Right, I'm going to state that this is 0. Well, I better prove that. Well, let's just look at the summation ai minus 1 over n. And this is I equals 1 to n, which equals the summation as I goes from 1 to n ai minus n lots of 1 over n minus 1. So why would the summation of ai be equal to 1? Well, let's think about it. I said that t is unbiased, which means the expected value of t is equal to mu. Well, let's think about that. The expected value of t equals the expected value, the summation as I goes from 1 to n, ai yi, which equals the summation as I goes from 1 to n, ai, the expected value of yi, which equals I goes from 1 to n, ai mu, which equals mu, I equals 1 to n ai. So this is only going to be unbiased if this equals 1. So let's go all the way back up here. I've got this is equal to 1. 1 minus 1 is 0. So let's just write down what we've got. We've got the variance of t equals, we said sigma squared. We've got the summation of ai minus 1 over n squared plus the summation as I goes from 1 to n, 1 over n squared. Let me just be a bit better on my summations, which equals sigma squared. We've got this summation as I goes from 1 to n, ai minus 1 over n squared plus, well, we've got n lots of 1 over n squared, so that's 1 over n. So we've got sigma squared on n. Well, blow me, this is the variance of y hat. So basically the variance of t equals sigma squared ai minus 1 over n squared plus the variance of y bar. Well, what's this? This is some number minus a number squared, so that's going to be positive. I'm going to add over a load of positive. So this, I don't know what it is, but it's greater than or equal to 0. So basically the variance of t is equal to this plus some non-negative number. So basically the variance of t must be greater than or equal. So this basically says that the variance of t is greater than or equal the variance of y bar. Okay, well, we can go one more step. We can say, well, when does it equal it? Well, it equals this when this thing here equals 0, which would basically mean that, well, sigma squared is greater than 0, so that can't be 0. So it must be the summation of ai minus 1 over n squared, I equals 1 to n equals 0. And that's only going to happen if ai equals 1 over n for all of them. Lovely. So there's your first indication of a proof where we basically go, I want to show the variance is something, this is the minimum, so I showed that it's greater than or equal to this number over here, sorted. It's also your first time, I think, I can't remember what we did last time, the first time where we actually started to use this add 0 trick as well. So that's it. We now know that the sample mean which you've been using all along was the best thing to do, which is a good thing. It's the blue. It's the best linear unbiased estimator. Okay, cool. See you next time.